Let's look at an advection initial value boundary problem in the first quadrant. So we're going to be taking our advection equation with constant speed 2, and it'll be homogeneous, so f is equal to 0. And we're in the first quadrant, so x and t are both positive. And we can take our initial condition to be e to the minus x, and our boundary condition to be 1 over 1 plus t squared, the Cauchy distribution. So let's see. So if we look at this situation, we know that our solution f, or we know that our solution u of xt from the previous sections is going to look like f of x minus ct by the method of characteristics. So the thing is, we're going to need to determine f separately for each of the two cases, either what's happening over here or what's happening over here on either side of this line x equals 2t. This is called the leading signal because it determines sort of where the behavior differs. So the idea for the solution is to let the PDE carry the boundary signal into the region. Oops. And so let me explain what I mean by that. So let's see. So what's going on the bottom? Along the bottom, we have something that looks like a decaying exponential. So it might look, as seen from above, something like this. Here it is, decaying down to 0. I'm imagining myself as being like up above the first quadrant and looking straight down. Meanwhile, over the t-axis, we have something that looks like a Cauchy distribution, so it goes down and there's an inflection point and then it tends to 0. Something kind of like that. Okay, so let's see then. So let's let the PDE carry this boundary data out into the middle of the region. So move it up a little bit more there. If we look at where x is bigger than 2t, then the characteristics come from the x-axis. And so what I mean is that if we look at stuff in this region here, these characteristics, and maybe I'll just make these, since they're not leading, some other color. So these characteristics here, they all have their origination point somewhere here on the x-axis. Okay. So if we look at the initial value, ux0, this is going to be f of x, which is e to the minus x. And so then that tells us that f of x minus ct is e to the minus x minus ct. Oop. On the other hand, for x less than 2t, so now we're in the upper half of this quadrant here, the characteristics come from the t-axis. So in this case, we've got u0t equal to f of minus 2t, which is 1 over 1 plus t squared. And so going back to the picture here, the idea here is that so we're looking at lines now that are up here. And in order to figure out what the formula is for those lines, we're going to extend them all the way down until we can see where they cross the x-axis down here. Okay, so we're looking at these points. All right, so well, now what? Okay, so we've got this, but it's not totally clear what f of x minus ct is at this point. So let's figure out what we need to do. So if we've got f of minus 2t is equal to 1 over 1 plus t squared, then if we do a change of variable and put s equal to minus 2t, so that minus s over 2 is equal to t, then f of s is going to be 1 over 1 plus s squared over 4. And so f of x minus ct is going to be 1 over 1 plus 1/4 x minus ct quantity squared. Okay, so that's what we have for the second part. And so our function in general, the solution to this equation, so this is our u. So this is going to be 1 over 1 plus 1/4 x minus ct squared for x up to 2t, and then it's going to be e to the minus x minus ct for x values after that. And so if we graph what this function looks like, so it's got something that looks like a Cauchy distribution, which is more or less kind of like a flattened bell curve that's going along this part right here. And then it's got a decaying exponential on the other side, so that's this part of the curve right here. So it actually looks a little bit like a water wave. Whoops. It looks a little bit like a water wave. There we go. Okay. And then we can ask what happens over time. Well, it's going to be propagated, so as we go forward in time, it's going to shift forward in space as well by speed c, I guess speed equal to 2 in this case. And then same thing, it'll shift both forward in time and space like this. And so the net effect is that we see this wave, and the discontinuity right along the ridge right here, or this point of non-differentiability, that's following our characteristic curve.